Not all electrical energy from the primary coil is transferred to the secondary coil. Although transformers are some of the most efficient units and have the most efficiency up to 99%, they're not perfect. And we do incur losses. One, losses due to the resistance of the coil of the wires, sometimes called copper losses. The second is hysteresis. It is the opposition of the ion to the changing magnetic field. Excuse me. Or the heat, the waste, the dreck. And then eddy currents. And eddy currents are usually that thin piece of steel laminated with varnish, using to insulate that metal, using soft steel which changes polarity easily. That helps with the hysteresis. So 3 losses: copper losses, hysteresis, and eddy currents. Okay, we will be dealing with losses shortly. Can I erase the board? Let's say here we have 20,000 turns, and we have a primary voltage of 2,400 volts. On our secondary side, we'll say that we have 1,000 turns with 360 amps given to us on our secondary side. Obviously, we would like to find the voltage of the secondary side and the current on the primary side. Take a moment and work it out yourselves right now. I'll work it out also, and then we'll review it together. We broke our turns ratios down. They wanted to find the voltage on the secondary side. We wrote our formula. We took out ES. ES equals EP times TS over TP. We put our values in the appropriate location. 2,400 times TS, which we broke down, instead of using 1,000, we broke it down to a simple value of 1. TP, we use 20, instead of using the whole number of 20,000. Too many zeros, so much room for making those silly mistakes. We found, obviously, this was a step down transformer. We had a 1 to 20 ratio based on the turns, 1 to 20, which means we stepped our voltage down 20 times, which means our current on our secondary side has to be 20 times greater than the current on the primary side. Or when using simple values, 360 divided by 20 would give you 18 amps. Again, we have a formula. We write our current formula. We realize IP was on the top half of the formula line. We look for what's on the bottom of the formula line. We take it, we flip it over. We take out IP, we rewrite our formula, we work it out, and we prove the 18 amps. Again, still dealing with no losses. Our primary power will equal our secondary power. Transformer, very good in auto. Again, cap off. In this case, they're telling me I have a 20 kW. I'm sorry, try that one more time. 20 kVA with 1,000 turns and a power factor of 100%. And you should always know this. The power factor will always be on the secondary side. On the primary side, we always see the efficiency. In this case, they're giving us an efficiency of 90%. 1,200 turns on the primary side, and they're giving us 120 volts. They're looking for the current in the common area, but we have other units in here now, such as the power factor, such as the efficiency. And one of the most important formulas that I can teach you is that the output is to the input times the efficiency. And I put a circle around this. The output represents the secondary side. The input represents the primary side. The input is always going to be expressed in watts. And we say that the output equals the rating times the power factor. The rating is always going to be expressed as what? kVA or VA. So the output is expressed in this case, kVA. Obviously, the K representing 1,000, so it's expressed in volt amps. And as we learned early in our AC theory program, the apparent power is expressed in volt amps. The true power is expressed in watts. The difference between the two of them is the power factor. So there will be times when we will have VA on our secondary side. They will give you a power factor, and it's a statement. The output equals the rating times the power factor, or 20,000 volt amps times 1, representing 100%, equals 20,000 watts. It's what gives us the ability to change from VA to watts up. Okay? What are we always looking for? We're always looking for the current in the common winding known as IC. Most auto transformer questions we get will always ask you for the current in the common winding. So we start out. I have a voltage. I have turns on the primary. I have turns on the secondary. I have no voltage. I need a voltage. I write a formula. I'll say voltage of the primary times turns of the secondary is to the voltage of the secondary times turns of the primary. I put a circle on this. First I needed to take 2 steps back. What didn't I do?
Ratio.
Thank you. My turns ratio. Or we say TP over TS. TP equals 1,200 turns over TS was 1,000 turns. The zeros cancel each other out. I now have 12 over 10. We look for a common value that goes into both of them evenly, such as the number 2. 2 goes into 12 6 times. 2 goes into 10 5 times. I can really say 6 over 5. 6 represents TP. 5 represents TS, and I put a little box around it. What am I looking for? Voltage on the secondary side. I take it out of the formula and I rewrite it. Voltage on the secondary side equals voltage of the primary times the turns of the secondary over the turns of the primary. Or simply we're saying, who? 120 times TS, which is 5, over TP is 6. Or 600 over 6 gives us 100 volts on our secondary side. We have the voltage on the secondary side. If I have the voltage, I look at my secondary side, what else do I have that would help me find current right now? Because I don't have the current on the primary side. Oh, I have power on the secondary side, and I have voltage on the secondary side. I can find the current on the secondary side. And simple formula right now by basically saying IS equals PS over ES. My power on my secondary side was 20 kVA, and I can say 20 kVA equals 20,000 volt amps. Or in this case, it's 20,000 over 100 volts is going to give me an amperage of 200 amps. I have everything on my secondary side that I need right now. I need to somehow get back over to the primary. Excuse me. I need to get back to the primary side right now. Well, wait, I have a new formula up there. The output, we know, was 20 kVA, or in this case, 20,000 volt amps, times the power factor, which is expressed as 100%, or 1. I now have 20,000 watts up. Better known as the output. They gave us the efficiency on the primary side. We can find the power or the input by taking out input. Input equals the output over the efficiency, or in this case it's 20,000 over 0.9. My input will always be greater than my output because there are no losses on the primary side. The losses occur as we come to the secondary side. So my input is really 22,222 watts up. I have the power on the primary side. They gave us the voltage on the primary side. We can find the current on the primary side by saying IP equals PP, power of the primary, over EP, voltage of the primary, or 22,222 over 120 volts is going to give us approximately 185 amps. The last part of this problem, we're looking for IC, current of the common winding, equals IS minus IP, or 200 minus 185 gives us what? 15 amps on the common winding being shared by both primary and secondary. It's all there for you. It's about looking to see what did they give me to work with. And as you ask yourself all the right questions, you should be able to get all the right answers. Especially if you're asking yourself, what? I want you to finish copying this, and we're going to do another one. %. The voltage is going to stay the same. What they're changing right now is the, power factor. How does this change everything? We no longer had 100%. They made it 80%. And you know what they're still looking for? Current in the common winding. So, we start out, and this is the first step. In this case, I see I have 20 kVA or 20,000 volt amps. That's the rating. We know that the output equals the rating times the power factor, or we can say 20 kVA equals 20,000 times 0.8, representing 80%. I now have 16,000 watts up. That was my first step. Realizing I don't have 20,000 watts. I only have 16,000 watts. I have a voltage. I have a wattage. I can find the water. I can say IS equals PS, power of the secondary, over ES, voltage of the secondary, or 16,000 over 100 gives me 160 amps. I have the current on the secondary side. I need to get back where? To the primary side. I have the efficiency. I have the output. I can take the input and say the input equals the output over the efficiency, or 16,000 over 0.9. We can say that the input's value is now 17,777 watts up. Obviously, we have the power on the primary side. We have the voltage on the primary side. We can find the current on the primary side by saying power of the primary over the voltage of the primary, or 17,777 over 120 gives us approximately 148 amps. And then, of course, the last part of the problem, IC equals IS minus IP, or 160 minus 148 gives us approximately 12 amps being shared by both primary and secondary one. It's not hard. It's not easy, but it's not hard. All right, it's not that easy, but it's not that hard. The important facts for you to remember is the efficiency will always be on the primary side, and the power factor will always be on the secondary side. And you're looking to see what information do you have. What's important is ultimately you're going to learn that all of the auto transformer questions always ask us the same thing. What is the current in the common winding? What do I have? I have a voltage, I have a power, I can find the current. We found the current. Simple formula. Current equals the power over the voltage. But in this case, it's the current in the secondary equals the power of the secondary over the voltage of the secondary. We calculate it, we find the right answer. What do we need to get back to the primary side? They gave me the efficiency. I have the output. I have the efficiency. When I have 2 of a 3-unit formula, I can find the input. We found the input. The input equaled the output over the efficiency. I have the power. I have the voltage. I can find the current. That's all that this is. Look at what tools they're giving you. All right, look at what units they're giving you to work with. Let's see what else.